Finally, we will discuss delusion in Cantor's diagonal argument, which will have 6 parts. First, I'll discuss what Cantor's diagonal argument is. In 1874, Cantor showed that C is larger than Aleph null by the method of nested intervals, and then reported that he had another proof by CDA in 1891. Even though CDA is promoted as the second proof that C is larger than Aleph null, what CDA itself discusses is that the cardinality of the power set of natural numbers is larger than that of natural numbers, such that 2 to the power of Aleph null is larger than Aleph null. That C is larger than Aleph null is not spelled out in the paper, but can be derived from C equals 2 to the power of Aleph null, which is based on Cauchy completeness. CDA is one of the cornerstones of modern mathematics and is considered as something beyond question. Professor Hodges, in 1998, writes that he dedicates the article "An editor recalls some hopeless papers" to the dozen-odd people whose reputations of CDA, I mean the one proving that the set of real numbers and the set of natural numbers have different cardinalities. However, a proposition that C is larger than Aleph null is different from a proposition that 2 to the power of Aleph null is larger than Aleph null. What CDA itself does is to prove 2 to the power of Aleph null is larger than Aleph null. He writes, "It has been around now for more than 100 years. Probably every professional mathematician alive today has studied it and found no fallacy in it. So there is every temptation to imagine that anybody who writes a paper attacking it must be of dangerously unsound mind. One should resist this temptation." He failed to mention Bertrand Russell. He passed away in 1970, however, who wrote an article critical of CDA in 1907. He writes, "It was surprising how many of our authors failed to realize that to attack an argument, you must find something wrong in it. Several authors believed that you can avoid the proof by simply doing something else. But I show logical flaws in CDA. What I challenge is not the proposition that C is larger than Aleph null. What I will show is that CDA has logical flaws in proving 2 to the power of Aleph null is larger than Aleph null. Then I will show that 2 to the power of Aleph null is equal to Aleph null." I will begin with an almost verbatim copy of the Google translation of the proof by Cantor. If M and W are two mutually exclusive characters, then we consider a set M of elements E, which is x of 1, x of 2, which depend on an infinite number of coordinates x of 1, x of 2, where each of these coordinates are either M or W. And let M be the totality of all elements E. Such a manifold M does not have the power of the sequence 1, 2, 3, meaning the cardinality of M is larger than the cardinality of natural numbers. In order to prove this, he'll show that if E sub 1, E sub 2, are any simply infinite sequences of elements of the manifold M, then there is always an element E sub 0 of M that does not correspond to any E, meaning that there is always an element M which is not in the listing. For proof, let E sub 1 equals A sub 1 1 A sub 1 2 dot 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 and E sub 2 equal to A sub 2 1 A 2 2 dot dot dot. Here the A sub U and V are M or W, and define a series B sub 1 B sub 2 dot 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 such that B sub V is equal to M or W but is different from A sub VV. That is, if A sub VV is M, then B sub V is W, and if A sub VV is W, then B sub V is M. If we consider the element E sub 0, which is B sub 1, B sub 2, dot dot dot, and then E sub 0 is not equal to E sub mu, then it follows that the totality of all elements of M cannot be put into the sequence E sub 1, E sub 2, dot dot dot, meaning that the totality of elements of M is larger than the sequence 1, 2, 3, dot dot dot. Otherwise, there will be a contradiction that E sub 0 is both an element of M as well as not being an element of M. However, his diagonal argument has led to many paradoxes. Cantor himself stated this paradox in his paper. This proof can be easily extended to the general proposition that the cardinalities of well-defined manifolds have no maximum, so that collection of all cardinalities forms a well-ordered crowd, so that in nature there is one next greater in every cardinality, but also a next greater one follows infinitely increasing set of cardinality, which can be expressed as this and will be presented in Cantor theorem in video 11D. Please send critical comments to this address. Thank you very much.